When we refer to an element in the periodic table, usually we use electron configuration. So let's use this shorthand. We'll start with Ne, and then we'll go 3s2, and then 3p2. We're going to try to figure out what atom that is. So we could redraw this. We'll start with the Ne right here, and then we're going to draw our S sublevel here. And if there's just one of those boxes, we'll call that an orbital. So, and then we're going to have another one right here. This is going to be the P sublevel. So a group of these things can be a sublevel, but each one of them is also just a single orbital. It turns out that the S sublevel has one orbital, and this P sublevel has 3 orbitals. But we're also going to try to fill it in with these electrons we have. 1, 2, 3, 4. Well, first we have our 2 from the S. So we're going to go 1 and then 2. We got 1 going up and 1 going down. And then 2 in this one. So we're going to go 1 here, and then we have to have 1 there. That's because we're following Hund's rule. Hund's rule forces us to use 1 electron per orbital until we kind of fill up the sublevel, and then we'll go back over and refill it in again. Going the other way though. We're pretty close to figuring out what this is. We could start from our neon on the periodic table, and then we can count up 4 spaces. So 1, 2, 3, 4, and we've reached silicon. So this is going to be Si for silicon. And of course we have to start filling in the electrons, and over here we'll call it the Lewis structure, but we're going to go 1, 2, 3, 4, and 5. And I was going in this sort of counterclockwise direction here, but I was also following Hund's rule there, the same thing that we did right here. It might be helpful to remember this pattern. 1, 2, 2, 3, 3, 4, dot there. 3, 4, 5, 4, 5, 6, 4, 5, 6, 7, 5, 6, 7, 8. If we match this up with letters, we would see S, S, P. This one's going to be an S and a P and an S. And then here we'll just have DPS, DPS. And here, this will start with an F, DPS, and an F, DPS. So as long as you remember how to DPS, you'll be good. Let's try to visualize the shapes of these sublevels. We'll start with the S. That's a sphere. It's got 2 electrons, and it's going to look something like that. The P would be dumbbell shaped, and it's going to have 6 electrons. It looks something more like this. The D sublevel is going to look more like a clover. It's going to have 10 electrons possible. It'll look something like this, kind of like the P, but a little bit more. And the F is going to look more like a sunflower. It has 14 electrons in it, and it'll look kind of more like this, something like that. It's pretty complicated, but if these ones here at the D0 or the F0, these ones kind of look more like donuts. So that's kind of interesting. Let's consider the amount of electron pairs that are within each one of these sublevels. So because there's 2 in that one, the S level only has 1 pair. In the P sublevel, of course, we would have 3 pairs. The D sublevel would have 5 pairs, and the F sublevel would have 7 pairs of electrons. Now the electrons are going to fill the lowest energy first. So when it comes to energy, S is going to be the lowest, then comes P, then comes D, and then comes F, usually. Now, sometimes the half-full sublevels are really stable, and so they'll prefer to take stuff away from other sublevels instead, if you can somehow manage to get a half-full sublevel. That's kind of an exception there. Electrons are trying to achieve a ground state, which is the configuration with the minimal energy. A side note on naming these, if you're using the p-axis method, you would take the axis that's normal to the nodal plane. So if this is the nodal plane, you'll take the axis as normal to it, and that is going to be your p-axis. For the d-axis method, you would take not the axis that's normal to the shape, All right, so here's our shape. And then here's the axis that is normal to it. Call that the x-axis. If that's the x-axis, then you would call this dyz. So you're not using that axis to name this. You might have to subtract the orbitals that are on the axis. Let's say you have your axis here and the orbitals happen to be right on it. Then you'd have to go d like x squared minus y squared if this is the x and y axis. So that's one way to name this. And the dz squared is the donut. That's how we name that one. If you wanted to specify a specific electron within an atom, you'd have to know its quantum numbers. And that's where the Pauli exclusion principle comes into play. There are 4 quantum numbers. The first one is going to be the principal quantum number, and this is Bn. This will refer to the energy level. You should be familiar with that one. The second one is the angular momentum number. This will be represented as L. Basically, if L is 0, then you're talking about the S sublevel. If L is 1, you're talking about the P sublevel. If it's 2, then you're talking about the D. And if it's 3, you're talking about the F. So it's not too complicated, you're just referring to one of these 4. The third quantum number is the magnetic number. We'll call that ML. And let's say we have 5 boxes here, because we are in the D sublevel. The magnetic number could go from negative L, negative 1, 0, 1, or positive L. Because remember that if we were in D, then the L would be 2. So there's negative 2, positive 2. This is just basically telling us which one of these boxes is that electron in. The fourth quantum number is spin, and that's written as ms. And this is going to be plus 1/2 if it's an up spin, or it would be negative 1/2 if it's a down spin, like that. And this is just basically telling us what's going on with those electrons. It's like an address. There's an equation that will give us the quantum numbers of an electron, and that's the Schrodinger equation. In these solutions, you're basically taking the total energy of one of these electrons, you're converting it to a wave function, and then you're squaring it. So that gives you a probability. Everything's positive. You're basically taking the total energy, converting that to a wave function, and that gives you the quantum state, the quantum numbers of that electron. This results in a probability distribution, or a percent chance of finding these electrons. Once you square the wave function, this is what the probability distributions look like, and this is for the 1s, 2s, or 3s sublevels. But over here, let's see, at this point, as a function of the radius, you'd have a percent chance of probability of finding something right here. This would be at 52.9 picometers. This is the Bohr radius. That's A0. So this is for the 1s, and in the 2s, you kind of have this little spot right here, which is a node. That's a 0% chance finding the electron there. You'd have a decent chance there, and a really good chance of finding it here. This is actually about 5A0. That's 5 times the Bohr radius. And in the 3s, you'd have a couple different peaks, but over here at the highest point, this would be about 9 of those Bohr radii. So this is just some different probability distributions and some examples of the solutions of the Schrodinger equation. Kind of cool. Let's have some fun drawing molecules. We'll go ahead and draw a water molecule here. Got the H's and the O. And I got 2 pairs of electrons going to be floating around over there. We're going to say that this has 4 groups of electron pairs, 1, 2, 3, and 4, even though those are bonds. Now we should know that the octet rule really only works for period 2 atoms. So once we get into the 3rd period, say for example like S sulfur, this thing can actually connect to 6 fluorine. So we're going to have 1 here, and I'm marking it going sort of crisscross patterns like this. And then this is going to be more like a wedge like this. And so these are sort of 6 fluorines. And these are a couple different ways that we can represent bonds and groups of electrons. Let's also consider the difference in the electronegativity between these two elements in order to figure out what type of bond it is. The electronegativity is highest when it's nearest to fluorine. These numbers will be found on the chart, but essentially if you take the difference between these two and you sort of calculate that, you'll know whether that bond is ionic, if that difference is greater than 1.7, whether it's polar covalent, which we're particularly interested in, at 1.7 to 0.5, being again that difference, and then non-polar bonds are going to be just less than 0.5, and the difference in electronegativity. Atoms and molecules, their electron orbitals, the wavelengths that they form, can actually overlap and interfere either constructively or destructive, depending on whether it's positive or positive and negative. If you have two positives combining, you'd have a bonding pair. You can imagine a nucleus over here that's positive and a nucleus over here that's positive, and some electrons that are negative in the middle. This would cancel out and balance, and this would be a very good, strong attraction. So this is going to require low energy, and so it's going to be stable. But let's say you have a little bit of a mess over here. This is a positive and negative anti-bonding pair. What would happen is you'd kind of have your positive nucleuses over here, and then the electrons would just happen to be over here on the outskirts and then kind of be stuck, and there'd be some repelling action here, and it'd be really difficult for this thing to be stable. This would require high amounts of energy to keep it together, and so it would generally be unstable. And so if you have more antibonds than bonds in a molecule, then it's quite possible that it can break apart with just a little bit amount of energy inputted. Now let's quickly fill out the VSEPR geometry chart. This is referring to the number of groups that are around the molecule like this, and the number of lone pairs. As you can see here, you'd have 2 lone pairs, whereas all these other ones are shared. And so across the top row, we would just have linear, and then trigonal planar, and then we have tetrahedral, trigonal, bipyramidal, and then we have octahedral. All these across the top are the ones that are the base names, so they would have 0 lone pairs. And of course, these are all going to be straight angles, so we have, well, actual real angles: 180, 120, 109.5, 90, 120, 180, and over here we have 90. So these are all like flat angles, essentially. Once you start getting lone pairs, those lone pairs could start to push the shared bonds in weird positions. So you'd get some strange shapes. You get things like bent, trigonal pyramid. This one's a seesaw. And then this one would be square pyramid. And so the angles here, they'd be sort of less than the original angle. You'd have less than 120. You'd have less than 109.5, less than 90, less than 120, but you'd still have the 180 degree one because it's a seesaw. And then you have the square pyramid, which is less than 90. All these on the first row have been pushed and altered in some way. Once you start getting 2 lone pairs, the pattern starts here. So you get the bent one, a T-shaped one, and then over here you'd have square planar. Here you'd have less than 109.5 significantly. You'd have less than 90. Here you'd get 90 exactly. And then the pattern continues down to here, so you get a linear shape here at this point at 180 degrees, a T shape here at less than 90, and the final one back to linear at the very bottom over here. And this completes our chart. Now these bond angles can have an effect on the polarity of these molecules. So let's say you had CO2 here. Well, these bonds are usually polar bonds. But since it's a linear molecule, the polarity of those bonds literally cancels out. And so this is a non-polar molecule. On the other hand, having lone pairs and having bent molecules like this definitely creates polarity. So like usually these things are going to be polar when you have these less than signs in the presence of lone pairs. Remember how this works. Since oxygen is more electronegative than the hydrogen, it's going to want those electrons, so it's going to be more negative. It's going to take the electrons away from the hydrogens. These things are going to be somewhat positive over here. And since this thing is all bent up like this, well, you're going to have like a negative side on this side and like a positive side on that side. And that's how you would get these lone pairs pushing these negative portions to one side and the positive portions to another side. The position and movements of electrons can have an impact on the magnetism of materials. So let's make a difference though between ferromagnetism, paramagnetism, and diamagnetism. Ferromagnetism comes from domains of electrons all lining up together, and so this becomes permanent because they basically get stuck in that shape. This is going to be really strong magnetism. Paramagnetism is when you might have unpaired electrons. This would cause a temporary magnetism in certain materials, but it's kind of a little bit hard to figure out whether something is paramagnetic. You have to use molecular orbital theory, because it turns out that silicon, even though it has 3 unpaired electrons, it's not paramagnetic when it becomes like a big solid. And O2 gas, even though when you make the Lewis structure of O2 gas, you won't find any unpaired electrons, but it turns out that is paramagnetic, just because you have to use molecular orbital theory to figure that out. But anyway, another kind of magnetism is diamagnetism, and everything's a little bit diamagnetic. Basically, when something is in a magnetic field, the electrons inside are going to try to spin around and create an induced field that's going to counter the magnetic field that they're in. And this is going to be a little bit repulsive. The thing is, though, this is really, really weak. So unless this is the only magnetism present, then the other kind of magnetism will basically overtake this. And so this is the consequences of electron configurations and stuff.